Okay, this problem says consider the learning curve, this function right here, which is a rational function because there's a variable in the denominator. P is the percent you get right, and N is the number of tries you get. For example, you could plug a 2 into this, and this will tell you the percent right after you get 2 tries at, let's say, a driving test. If you plug 5 into N, that would tell you how many percent you get right after 5 tries, and so on. Now, what we need to do is we need to simplify this a little bit. So to simplify this, I would take the 0.7 through, and I get 0.7n, and take the 0.7 times the minus 1, I get minus 0.7, and minus 0.7 plus 0.5 is a minus 0.2. Take the 0.8 through, and you get 0.8n. 0.8 times minus 1 is minus 0.8, negative 0.8, and negative 0.8 plus 1 is positive 0.2. So now that it's simplified, I just need to type in my coefficients into the Excel sheet. So my coefficients for the numerator are 0.7 and minus 0.2, and for the denominator 0.8 and positive 0.2. And they're in here. And this is my linear coefficient. Here's my constant for my numerator. And in the denominator I had 0.8n plus 0.2. So they're in there now. Now we could see how many you would get right after any number of tries. When you're putting a number for x here, you're putting in the number of attempts. So after 1,000 attempts, you can see the person gets about 87.5% correct. And in fact, that's what this graph does. It levels off here, and it's leveling off to a horizontal asymptote of 0.875. So as your number of attempts are approaching infinity, your percent correct is approaching 0.875 or 87.5%. You'll never get above that. That's as high as it goes according to this equation. Now, if you want to find, for example, when will you get 70% correct? Well, you would just type 0.7 in here, and then hit enter and click the find solutions, and you'll get the solution. You'll get 70%, or actually more than 70%, when you take 3 tries. You can't take 2.42 tries. When will you get 80% correct? Well, you'll get 80% correct at exactly 6 tries. You could plug the 6 in here, and we better get 80%. Okay, back to the horizontal asymptote 1 second. You're going to have problems sometimes that you need to find the horizontal asymptote by hand because it's going to be higher than a cubic over a cubic. Now, how would we do that on this particular problem? Well, let's say we didn't have Excel. We would simplify it, and then we would look at the numerator, whose power is to the first power, and the denominator, whose power is to the first power. Now, if I refer back to the first page of notes for this section, let me back up to there. The first page of notes tells us how to find x-intercepts, which are also known as roots. You find them by setting the numerator equal to 0. Like, for example, this function right here would have a x-intercept at 3/2 because you set the 2x minus 3 equal to 0. How to find horizontal asymptotes? Well, how to find horizontal asymptotes algebraically right here is what we're talking about. And if the power of the numerator equals the power of the denominator, then the horizontal asymptote is located at the leading coefficient of the numerator over the leading coefficient of the denominator. And that's what we have going on with this problem, is the power of the numerator is 1 and the power of the denominator is 1 on the problem we're dealing with the number of attempts. So we just divide the 2 leading coefficients. But this is a handy-dandy sheet to have handy. For example, if the power of the denominator is greater than the power of the numerator, then you have a horizontal asymptote on the x-axis at y equals 0. And if the power of the numerator is greater than the power of the denominator, then you don't have a horizontal asymptote. Let's go back to our problem. For our problem, we can see they're both to the same power, so we just take the leading coefficients to divide them. And if you divide 0.7 by 0.8, you'll get 0.875. So let's go ahead and go on to the next problem. Okay, on this problem it says write the equation of a rational function in the form f of x equals ax plus b over x plus c that has a horizontal asymptote at y equals 30, an x-intercept at 3, well 3 comma 0, and a vertical asymptote at x equals 3. Well, let's go ahead and start substituting some things in. If this is x plus c on the bottom, then the leading coefficient on the bottom is 1. Now, we have a horizontal asymptote at 30. So that means that the ratio of a, the leading coefficient here, divided by 1 is 30. So what number divided by 1 gives you 30? Well, 30 divided by 1 gives you 30. So the a must be 30. Okay. Now to get the b, you use the information about the x-intercept. The x value of the x-intercept is 3. You find the x-intercept by setting the numerator equal to 0. So if I set 30 times 3 plus b equal to 0 and solve it for b, I'll get b equals negative 90. So that's what the b is. Now, in the same way, you find vertical asymptotes by setting the denominator equal to 0. So if I set x plus c equal to 0 and solve it for c, I'll find out what c is. I know my vertical asymptote is at 5, so if I say 5 plus c equals 0, I can solve it and I get c equals negative 5. So that's what the c is. Now if I graph this, I should have these features: a horizontal asymptote at 30, an x-intercept at 3, 0, and a vertical asymptote at 5. Well, let's take a look at that. Okay, that equation was 30x minus 90 over x minus 5. So I put in my coefficients here, and I graphed it from negative 13 to 10. And what do I get? Well, I clicked on this button. You got to click on here to get your x-intercepts, and they're at 3. I got a vertical asymptote at 5 and a horizontal asymptote at 30. And I can see that here's my vertical asymptote right here at 5. That's where the graph goes vertical. And if you want to find max mins or what it's leveling off to, get away from your vertical asymptote. So let's graph this, let's say from 6 to 10. If I graph this from 6 to 10, you can see it's coming down, leveling off to how high? Well, it will be 30. Let me go out farther. Let's go out to about 100 or so. And now if I look at it, it's leveling off to 100. And that's what that graph looks like. So that matches up with what I had before, what I got right there. And again, you can check it by setting this equation. If you set the numerator equal to 0, you'll get the x-intercept. Set the denominator equal to 0, you'll get the vertical asymptote. And if the powers are the same, divide them. Divide the leading coefficients, and you'll get the horizontal asymptote, which is 30. Now in this problem, part B, it says that if a rational function has a horizontal asymptote of y equals 0, an x-intercept, and the variable in the denominator is the second power, what is the power of the numerator? Well, if the power of the denominator is to the second power in the denominator, and there's a horizontal asymptote of y equals 0, then the power of the numerator must also be to the second. Well, no, it would have to be to the first or 0 power, because to have a horizontal asymptote, the power of the numerator must be smaller than the power of the denominator. So it would either be to the 0 or first power, and then it has an x-intercept, so it can't be to the 0 power, so it has to be to the first power. Now this one, it says if a rational function does not have a horizontal asymptote, has a vertical asymptote, and the variable of the numerator is to the second power, what is the power of the denominator? Well, if this function does not have a horizontal asymptote, then that means that the power of the numerator is higher than the power of the denominator. Okay, well, the power of the numerator is the second power, so that's higher. That is higher than the power of the denominator. So the denominator must be either to the 0 or to the first power. Now it has that vertical asymptote, so there must be a variable down in the denominator, so it has to be therefore to the first power. And that will wrap it up with this section.